Hello, party people. This is our first of 3 videos for our 4C and 4D retake. This one we are going to focus on 4C, which is all about our gas laws. Alright, so, think about those gases. So we're going to kind of talk about the qualitative, which is like when one increases, the other decreases, and why does that happen? And we're going to do one problem just on the math part as well, so you see some examples of that. So there are 3 gas laws we studied. Before we get to those, actually, part of this standard is also one-step conversions. So just real quick review. If I want to go from 3.5 ATM and convert that to torr, I start with my 3.5 ATM. I multiply by my conversion factor. Remember, this is over 1. You can write that or not, whatever helps you. I need to get rid of the ATM unit, so I put that on bottom. I need to go to the torr unit, so I put that on top. I know from my equation sheet or my memory that 1 atmosphere is equal to 760 torr. And a conversion factor, top and bottom, must always be equal. So that means 760 torr is equal to 1 ATM. ATM cancels. You multiply these, which you can do the long way, but I'm just saving some time here. And you get 2,660 torr. Okay. If you went the other direction, you'd have to have torr on the bottom, so this whole thing would have to be flipped over. But we didn't go that way, so we didn't do it that way. Okay, now we're getting to the gas laws. So Boyle's law is about pressure versus volume, assuming that temperature is constant. If temperature is not constant, it doesn't work. And so if you graph pressure versus volume, you get a very kind of predictable shape in this hyperbola. I don't know if you know that vocab word, but what it shows is that as volume goes up, pressure is going down. So if I can try to show this with my drawing here, I have a box. Let's say that we have 4 gas particles in it. If these gas particles are moving around, and as they move around, they bump into the surface, and every time they bump, they're creating pressure. So if they don't change speed, but you increase the volume, moving the same speed, constant temperature, it's going to take a lot longer bump for it to hit the surface and create that pressure. So the bigger the volume, the slower it's going to hit and the lower the pressure. So that's Boyle's law. Charles' law is comparing volume and temperature, and this is assuming you have a constant pressure. So if you graph it, you get a shape, and then again, this is only true for a Kelvin temperature, which is why you might see a K sometimes. You get this line like this. It's supposed to be straight, but I can't draw straight things. I don't know why. So this is directly proportional. When one goes up, the other goes up. So again, if we think about this, this should hopefully make sense. If the pressure is constant, that means the number of collisions with the surface always stays the same. Well, temperature relates to how fast particles move. So if temperature's, if the temperature's something and particles are moving this fast, and then you start to increase the temperature, they start to move a lot faster. Well, now they're colliding more, but it says pressure's constant. Well, the only way for the pressure to be constant is if the volume gets bigger as well. So now, even though the particle's moving faster, it still ends up making the same number of collisions because it has to travel farther to hit the surface. So the only way pressure can be constant is if pressure and volume, or temperature and volume, go with each other. So if the volume shrinks, that means the temperature must have shrunk too. Otherwise, the pressure would change. Last one is Gay-Lussac's law, which is pressure and temperature, and this is with a constant volume. So now I can't change the size of my box. The volume's constant. And the shape of this on a graph, again, this would be for Kelvin temperature, would be this directly proportional relationship. When one goes up, the other goes up. So if you think about increasing the temperature, here's my particle, it's moving, I suddenly increase the temperature, it's going to hit the surface a lot more, so the pressure goes with temperature. Okay, if we look at an example problem here, and again this is for 4C, first thing I always do is I annotate. So let's annotate. A popcorn bag has 0.5 liters of air in it at 27 Celsius. I know already I'm going to have to convert that to Kelvin, so I add 273. The air is heated up by 100 Celsius. Okay, by 100 Celsius. How much space, I know space is volume, does the bag take up at a constant pressure? So I'm going to be able to cancel out P. So after I annotate, then I want to collect my variables. So I know that my initial volume is 0.5 liters. My initial temperature is 27 degrees Celsius, which I have to convert to Kelvin, because like I just said, all these graphs are only true for Kelvin. It says the air is heated up by 100, which means I have 300 plus 100, so that's 400 Kelvin. And then it's asking me for V2. It's asking me for how much space. So my combined gas law is P1V1 over T1 equals P2V2 over T2. Pressure's constant, so I can get rid of that. And then I just plug in. So I have 0.5 liters over T1, which is 300 Kelvin, equals V2, I don't know what it is, over 400 Kelvin. Do I have to cross multiply? No! You only cross multiply when the variable you're looking for is in the denominator, like that, which isn't the case. So all I have to do is the opposite of what's currently happening to V2. So currently V2 is getting multiplied by 400 Kelvin. I'm sorry, divided by 400 Kelvin. So I'm going to multiply by 400 Kelvin. That's going to cause this to divide out and leave me with V2 by itself. So Kelvin divides out. I can divide top and bottom by 100. I get 4 times 0.5 gives me 2 over the 3's still left over, and there's my V2. Let's see, this should make sense. I'm increasing the temperature, so the volume should be going up, and 2/3 is about 0.6. So yes, the volume went up, so that's good. All right, come to class ready to learn, ready to participate, ready to work in groups, and we are going to get better at these standards.